We're going to start with step one, which is how do you tell a cat from a dog? All right, so this was a big thing like a dozen years ago. Cats and dogs are similar. Can a program tell a picture of one from a picture of another, right? So if you take just a few measurements, like, can you find the eyes or something, that doesn't work because they both have eyes, they both have snouts, that kind of thing just doesn't get you anywhere. If you take a whole bunch of little statistical measurements, like, how blue is the corner and how many parallel lines are there in the center, whatever it is, just some really simple stuff, that doesn't tell you. But let's say you take all those little measurements. We're going to give them a ridiculous name. We're going to call each measurement a neuron, okay? I'm saying ridiculous because we don't even know how biological neurons really work for sure, but we're going to call these things neurons. All right. Now, that doesn't work, but then you put up another layer, and that one does measurements of the previous layer. And then you put up another one, and you make a big pile of them, like a skyscraper, of layers of measurements of measurements of measurements. It turns out, if you make a big pile like that, it can start to work. That's called deep. So when you hear deep learning, that means there's a bunch of layers, right? Doesn't work at first, you have to train it. What training means is that you keep on running it and telling how well it did, and whenever it does better, you kind of add a little what's called a weight, a little indicator to some of the neurons that they're doing a good job, and then you can pull back some of the other ones. And once you do enough of that, you have a trained model, okay? And that works. Now, it might feel weird that that should work. Two things about that. One is we don't really understand why it works in detail. We're just starting to have, in some special cases, some ways of understanding why one weight matters versus another and what it means. That's all very new. It's kind of a craft in a way. It's a technique that works. But the thing I want to suggest is that it would be even weirder if it didn't work. Like, wouldn't it be weird if a bunch of statistical measurements couldn't tell a dog from a cat? Like, it should work at some point because statistics is real. All you need to do is find the right configuration to get you there, and this is it, so far as we know. So that's step one. Is that all clear? Yeah. Step two, do that, but for everything. So, so what you do is you take in the whole internet and every other piece of data you can possibly grab, and then you think that adjacency is going to have some correlation with meaning. So if there's like some text next to an image, maybe the text and the image have something to do with one another. So in the OpenAI or Microsoft world, the thing that does all that is called CLIP. We take in literally billions of these examples, and we try to do exactly the same thing I said about cats and dogs for everything everywhere. And that's called the large model, okay? So now, instead of just one tower of these things that can tell cats from dogs, you have this huge mush of towers that are there in the waiting, and when you need a tower, it might be there. It probably will be there if there were enough examples. So one of the towers might distinguish whether language is like pirate talk or not, and another one might distinguish whether it's a flying saucer or not, whatever. And we don't even really know what all's in there because it's too giant. It's this huge big thing. Super expensive to calculate, but that's what we do. That's the large model. Okay. Ready for step three?
Yes.
Step three, you run the thing in reverse. And I'm going to do this with images, but something analogous happens with text and music and computer code and everything. So with images, we're going to start with a field of snow, of randomness, right? And now what you're going to do is you're going to add some more randomness to the randomness. Now that sounds useless, doesn't it?
Yes, it does.
It does, but it isn't. And the reason why is you add some randomness and then you're going to run it by one of these towers. Let's say the one that can find cats. And if the different randomness is a little bit better at finding a cat, it triggers the cat detector. We call this a classifier. A catifier. Anyway, if it starts pinging, you save that. And if it gets worse, you throw it away. And then you do that over and over and over again, and out of the snow emerges a cat. Okay, now, and that works, and it'd be weird if it didn't work, right? I mean, so now we're at the point of generation, but we're not done. The magic is that you can have it solve for multiple classifiers at once. And this is where we hit something new. Now, you've probably seen some people, like my friends Timnit Gerbu forgetting his name. Another friend of mine wrote a piece in the New Yorker, your sister Mag, talking about how all AI can do is regurgitate sort of randomly. Timnit called it stochastic parrots. Is Timnit here? So this is true. This is what it does. But the trick, the thing that's really new, is that you can solve for multiple classifiers at once. So you can say, can you give me a cat that's using a parachute and playing the banjo and is dressed in Western wear and the whole thing's a watercolor or something. You know, just the kinds of crazy prompts that people send to programs like DALL-E or Midjourney or, you know, Stable. You do that, and it's round-robining through all of them. It has to address all of them at once for the image to come out of the snow. And here's what's amazing. It has to stochastically explore ways of addressing all the classifiers at the same time. And in doing that, it solves problems. And it's a form of creativity. Like, if a cat's wearing a parachute, how exactly does the parachute go on the cat? What is the cat's posture? How exactly does a cat hold a banjo? All right? No, I mean, these are actual, like, if you were doing that, you'd have to think through those things. This happens just in order to meet all the classifiers. Generally, sometimes it just screws up and gives you nonsense, but generally it starts to find these things. So what I propose here is that we can understand what generative AI does, and here's where this is going to get into something new, as filling in the space between the towers. So what happens is you have one tower for cat, one tower for parachutes, another tower for banjos. Previously, there was a space between them, and now, in order to generate, it fills in that space with something that meets all of them at once. So what's nice about this intuition is it both shows what's special about this, but also its limits. It goes up to the level of the towers, but it's unlikely to go much higher. Now, I know some people who are very pro-AI, whatever that means, will say, but do people go above the towers? I don't know. That's not my point here. The point is to talk about what the technology can do. And so what the technology can do is it can fill in between the towers, and yet we shouldn't expect it to grow beyond the towers. So the people who say, oh, it's going to become super intelligent and solve global warming, so we don't have to worry about that, let's just build AI. No. All it can do is reconcile towers that we've already defined, that we've already worked on enough that they're solid. Now, that's an incredible value. Like when you program, you're inevitably tediously reconstructing something similar to things that people have done millions of times before, and it's painfully tedious. Well, with generative AI, you can leverage all those previous times and get a version that matches your circumstance and saves you a bunch of time. That's filling in this space between the towers. So AI does something, filling in the space between the towers, but not everything, which is climbing way up above the existing towers. And there you are.
I like it.